Hello, welcome to this video for example 4. In this example, we have a 6-year loan of $26,000 with a 6.5% annual interest, compounded monthly. If the borrower were to add $100 per month to the normal payment, after how many payments will the loan be completely paid off? So let's take this one step at a time. This is a multi-step problem, and so let's just do one thing at a time. First of all, the very first thing we need to do is compute the normal payment amount before they add this $100 extra to pay the loan off early. So we're going back to the loan payment formula, which originally was in this form here with the principal of the loan, P, on the left side. And then on a previous slide, we noted that we can rearrange this algebraically to get the payment on the left and the principal or the initial balance of the loan over here on the right. So we're going to use this version because this is going to give us the payment that is required to pay the loan off in the normal amount of time. So the original principal was $26,000, capital P is this. We multiply that by the rate, which is 0.065. That's the numerator. And then in the denominator, we have this thing here, K times this big quantity. K is 12 because we have monthly payments. And then we fill in the rest. And then using a nice calculator, then we get the payment of $437 and about 6 cents. So we're going to always round that to the nearest penny when we talk about payments like this, because this is money. You can't send a check for this amount of money to the bank. So we're going to round this to 6 cents. So the normal payment is $437.06. So that means the borrower is actually paying $537.06 per month because they're adding $100 each month. So we're going to use this amount as the actual payment amount to solve for the time T required to pay off the loan. So that's our next step. So first step, find the regular loan amount, add the $100 to it, and then use that as the normal payment, right, in our loan. So now we're going to use the other version of the formula where we have the payment over here on the right, and capital P on the left. It probably doesn't matter which version you use because remember the ultimate idea here is to solve for T, but at least this version puts the T up here in the numerator, which will make it a little bit easier to solve algebraically. So all of the other values for R and K and T are all the same with the exception that we don't know T. So we're going to leave that alone, but now we know the payment, and that's $537.06. So we fill in the payment, we fill in the loan balance of $26,000 over here on the left, we fill in the rate, and we fill in the value of K. And then we have to solve for T. So that leaves us with an algebraic dilemma. So keep in mind that we have to isolate this T all by itself. So the first thing I'm going to do is get rid of this denominator here by multiplying 0.065 divided by 12 on both sides of the equation. And that's what we see over here in blue, multiplying the left and the right. Now, on the right side, these two items here, this one here and this one in the denominator, are going to divide out. And that's going to leave me with this expression on the right-hand side. So the fraction has been simplified and there's no longer a fraction. And we have this kind of ugly thing. And then over on the left-hand side, we have what we have here. Okay, so we're going to keep going. Remember, we're trying to isolate T all by itself. So there's all this other stuff that we have to get rid of. And we're going to work from the thing that's furthest away. So let's keep going here. And so our next step is to get rid of the 537.06 that's on both sides. That is kind of furthest away from this T that's way out over here. So I'm going to divide both sides of the equation by that. So that's what I'm doing in this next step. On the right side, the 537.06 in the numerator and in the denominator are going to divide out to 1. Leaving me with just this expression that's inside this larger group of parentheses, 1 minus the quantity, 1 plus 0.065 over 12, to the power of negative 12t. And then on the left, we have this complicated expression here. But remember, we've got calculators to do all this for us. So we're just going to keep it in this form and keep going until we get the t variable completely isolated. Okay, so continuing to isolate the t on the right side, we got to get rid of this 1 here. So I'm going to subtract 1 from both sides. And so there's a couple steps that are taking place here. You'll notice that I've subtracted 1 from the left-hand side here, and I've subtracted the 1 from over here on the right side. And the problem with that is that it leaves me with this negative sign in front of this expression, the 1 plus 0.065 over 12 to the negative 12t. That's coming from the original expression right here. So once I get rid of this 1 right here, I still have this negative here. So now I'm going to get rid of that by multiplying both sides by a negative 1. Now, when I multiply the left side by negative 1, so if I distribute this negative 1 into these two terms, notice it just flips the sign of each one. So negative 1 times this negative 1 becomes positive 1. And then negative 1 times this fraction becomes that negative fraction. Over here on the right-hand side, the negative sign that we were, so to speak, stuck with now changes because this negative times this negative makes the right-hand side expression completely positive. Okay, so continuing the process, we have negative 12t is the power. Remember that the way that we can get or solve for variables that are in the exponent position is to use logarithms. So the next step is to take the logarithm of both sides. Do it to one side, do it to the other. So that's all I'm doing here is taking the log of both sides. And remember, we have that rule that says that if you have the log of something to a power, then that power, excuse me, can move in front of the logarithm as a factor, a multiplying factor. So that's what I'm going to do here is move this negative 12t in front of the log over here on this right side. The left side just stays the same because we're just taking the log of this big, ugly expression. So we're almost there. We have negative 12 times t times the log of this thing. And keep in mind that this logarithm here, this is just a number. And so is the negative 12. So if I want to isolate the t, I can divide by both the negative 12 and the logarithm of this thing, because they're both just fixed numbers, and that's going to isolate the t for me. So that's essentially our last step, is to divide both sides by the negative 12 and the logarithm of that number. And over here on the right-hand side, the negative 12 over negative 12 goes to 1. The logarithm divided by the logarithm also goes to 1, and that leaves this t all by itself on one side of the equation. The other side of the equation is this kind of intimidating looking expression, but again, with a scientific calculator, that we can easily put that into that calculator, and out comes this expression. So t is 4.6914. Now keep in mind, t is always measured in years, and so we're going to have to do a little bit of mathematics to get to months, because that's the number of, or that's the how we're paying this off is monthly. So if I take the number of years and multiply by 12 months in a year, I get 56.29. So it's going to take 56 full payments and 1 partial payment. So technically, it would take 57 payments, the last one being only a partial payment, where you pay off whatever remaining balance is left after the 56th payment.